Hello friend, myself Mr. Uttam Gawali, RBNB College, Srampur. Today we will discuss a topic divisibility. First we see the definition of divisibility. Here an integer b is said to be divisible by a non-zero integer a if there exists an integer x such that b is equal to ax, and this is written as we write a divides b. In case b is not divisible by an integer a, then we write a does not divide b, and the property a divides b may also expressed by saying that a divides b, or a is divisor of b, or b is multiple of a. Here we see some note: if a divides b and 0 is strictly less than a is strictly less than b, then a is proper divisors of b. Now here we see some theorem on divisibility. Here we see theorem first: if a divides b, then a divides bc for any integer c. Now see proof. Here given that a divides b. Now by definition of divisibility, there exists an integer, say small x, such that b is equal to a into x, and given that c is any arbitrary integer and c is any integer. So multiply both sides of b is equal to ax by c. We get b into c is equal to a into c into x, a into c into x, and we rewrite a into c into x by a into c into x is equal to a into q, where q is equal to c into x, and here given c is any arbitrary integer and x is also integer, so c into x is also integer, implies q is equal to c into x belongs to z, and that is here we prove bc is equal to a into q. And by definition of divisibility, if we remove q, then it can be symbolically denoted by a divides bc. Here a divides bc. Now hence the proof. Okay? Now second we prove theorem second. Now here prove theorem second: if a divides b and b divides c, then a divides c. Now proof of this theorem. Now given that a divides b and b divides c. Now definition of divisibility: if a divides b, then there is integer, say q1, and b divides c, then by using again definition of divisibility, there is integer, say q2. Now by definition of divisibility, there exists an integer, say q1 and q2 such that b is equal to a into q1, say equation number first, and c is equal to b into q2, say equation number 2. Now by definition of divisibility, there is two integers satisfy. B is equal to a into q1, say equation number first, and c is equal to b into q2, say equation number second. By equation first we get values of b, put in this equation second. Now put equation 1 in equation second. We get c is equal to a into q1 into q2, and we rewrite this a into q1 into q2 is equal to a into q1, where q is equal to q1 into q2, and by definition of divisibility there exist two integers q1 and q2, therefore multiplication of q1 and q2 is also integer, therefore q is equal to q1 into q2 is also belongs to z. That is, here we prove c is equal to a into q, and by using definition of divisibility, if we remove that integer, then it can be symbolically denoted by a divides c, then hence the proof. Now here we see some next theorem. So theorem third. Now here we prove theorem third. If a divides b and a divides c, then a divides bx plus cy for any integer x and y. Now see proof. Given that a divides b and a divides c. Now again, by using definition of divisibility, by definition of divisibility, there exists an integer, say q1 and q2, such that b is equal to a into q1, say equation number first, and c is equal to a into q2, see equation number second. Now multiply equation first by x and equation second by y. Now here multiply equation 1 by x and multiply equation second by y for any integer x and y. We get bx is equal to a into x into q1 and cy is equal to a into y into q2. Say equation number 3 and say equation number 4. Now adding these two equation 3 and 4, adding equation 3 and equation 4, we get, adding equation 3 and equation 4, we get bx plus cy is equal to a into x into q1 plus a into y into q2. Here right side of this equation, a is common of both term. Now a into x into q1 plus y into q2 is equal to a into q, where q is equal to x into q1 plus y into q2. Now given x and y both are integers and there exist two integer q1 and q2, both are integers, so x into q1 is also integer, y into q2 is also integer. Again x into q1 plus y into q2 is integer. That is Q is equal to x into Q1 plus y into Q2 belongs to Z, and here we prove Bx plus Cy is equal to A into Q, and by using definition of divisibility, if we remove Q, then it can be symbolically denoted by A divides Bx plus Cy, hence the proof. A divides Here we see next theorem, theorem 4. If A divides B and B is not equal to 0, then absolute value of A is less than or equal to absolute value of B. Now see proof. Given A divides B and B is not equal to 0. Therefore, by using definition of divisibility, there exists an integer, say Q, such that B is equal to A into Q. Say equation number first. But given that B is not equal to 0, that is left side of equation 1 is not equal to 0, so right side of equation 1 is also not equal to 0, and by using definition of divisibility, A is non-zero integer implies B is also implies Q is also not equal to 0 and Q belongs to integer, hence Q is greater than or equal to 1. Now taking absolute value, we get absolute value of Q is greater than or equal to 1. Now multiply this equation both sides by absolute value of A. This implies absolute value of A into absolute value of Q is greater than or equal to absolute value of A, and we rewrite this equation as absolute value of A is less than or equal to absolute value of A into absolute value of Q is equal to absolute value of A into Q. But by equation 1, A into Q is equal to B. Put this value in this equation, implies absolute value of A is less than or equal to absolute value of B. Now hence the proof. Now we'll see next theorem. Now here we see next theorem, theorem 5. If A divides B and B divides A, then A is equal to plus or minus B. Now proof. Given A divides B and B divides A, but we know that if A divides B, then absolute value of A is less than or equal to absolute value of B, and if B divides A, then absolute value of B is less than or equal to absolute value of A. Now this put in this equation, say equation first and equation second. Now equation first and equation second. By equation first and equation second implies A is equal to plus or minus B, or absolute value of A is equal to absolute value of B implies A is equal to plus or minus B, hence the proof.